Hello, my name is Debashree ADDI and I'm here to present my final year project on classification of deepfakes and beautified media through this video demonstration. Let's start by discussing the problem statement. Recently, videos and images have known to be manipulated using deep learning to generate fake videos and images which appear to be real, widely known as deepfakes. These deepfakes are a cause for high concern as they tend to disrupt the integrity of videos in the form of financial frauds, hoaxes, and fake news. Here is an image which shows how realistic fake images can be generated using generative adversarial networks by face swapping technique. Many deepfake detection models have been developed which detect fake and real digital media accurately. Along with deepfakes, another category known as beautified media has also arisen as a result of digital manipulation. This media consists of images or videos that have been processed through addition of filters, makeup, or smoothened skin. This beautified media may be mistakenly classified as a deepfake by deepfake detection algorithms, whereas they are just real videos and images with an added filter. This creates a need to develop a model to accurately differentiate between real, fake, and beautified media. The objective of this project is to present experiments using the CNN model exception with a large dataset of labeled real, fake, and beautified videos to give a highly accurate image classification result. The first step was to generate and collect the required dataset for model training. The face forensics dataset was used to collect original and deepfake videos. Face forensics is a forensics dataset consisting of original video sequences that have been digitally manipulated with four automated face manipulation methods: deepfakes, face-to-face, face swap, and neural textures. On the other hand, the beautified data was generated using Beauty Camera, a Python based image processing application that can convert existing images to their beautified version. Three degrees of beauty filter intensities, third, seventh, and 10th, were chosen in order to test the model's classification performance with different levels of filter intensity in the beautified dataset. The first step for dataset preprocessing was to capture frames from the fake and original videos in order to train our model with images. To capture images from the videos with faces in them, it was required to process the videos through a face recognition function. With the usage of face recognition Python package and OpenCV's video capture function, a folder with cropped face images from a frame in each video was generated for both real and fake categories. Frames on which the face recognition didn't successfully work were removed from the dataset as it would cause irrelevant noise. The beautified data consists of cropped face images of the original data with the beautified filter. The final data looked like the images shown for each category on the slide. Next step of dataset preprocessing was to generate edge map of the images in the dataset and feed it into the model in order to compare performance. Edge map of images were generated using Canny algorithm through OpenCV's Canny function. The edge map and the image both were concatenated in order to input into the exception model. Similar to the edge map generation, Laplacian gradient of the images were generated to improve model performance. These were generated with OpenCV's Laplacian image gradient filter. The Laplacian gradient of the image and the image were both concatenated in order to input into the exception model. The exception CNN architecture comprises of 36 convolutional layers pre-trained with the ImageNet dataset. The exception model was trained on three different kinds of inputs to compare performances: only image dataset, image concatenated with its edge map dataset, and image concatenated with its Laplacian gradient dataset. The classifier was trained with dataset labeled as three classes: real, fake, and beautified. The label mode was categorical. Batch size was set to be 32 and image size as 256 by 256. It was instantiated with no weights, input shape as 256 by 256 by 3, and three classes. For each layer in the model, L2 kernel regularizer had been added with a factor of 0.001. The model was then compiled with Adam optimizer and mean squared error as the loss function and further trained for 200 epochs. The training, validation, and the test dataset consist of 70, 20, and 10% of the dataset, respectively. Model was trained and evaluated with 3 degrees of beautification filter, 3rd, 7th, and 10th in the beautified data to compare accuracy. Model was also trained and evaluated with 3 types of datasets, which are only image dataset, image concatenated with its edge map dataset, and image concatenated with its law placing gradient dataset. The training and validation accuracy plots for model trained with 3 degrees of beautification filter in the beautified data is shown here. On comparison, we can observe that the model performance improves slightly as the degree of beautification filter increases. This incremental change in the accuracy is expected because a lower degree of beautification filter intensity is harder for the model as compared to a higher intensity of the filter to detect an image under beautified category. Hence, it is better to improve model performance for the dataset with third degree of intensity because if the model performs well for lower degree of filter intensity means it will probably perform better for a higher degree of filter intensity. The training and validation accuracy plots for model trained with 3 types of pre-processed datasets, which is only image dataset, image concatenated with its edge map dataset, and image concatenated with its law placing gradient dataset is shown here. We can observe from the plots in the above section that the comparison illustrated in the table that the model performs a lot worse for the dataset of images concatenated with its edge map as compared to the only image dataset. The reason for this could be that the edge map of the image didn't contribute to a lot of useful information for the model to train on. However, the model trained on the dataset of images concatenated with its law placing gradient performed a lot better than the only image dataset. This is mostly because law placing gradient pays in-depth attention to the edges and details as compared to canny edge map. Hence, the best model accuracy is for the law placing gradient dataset with an accuracy of 0.8962. Final result is that the best model accuracy of approximately 89% is given by exception CNN, which was trained with dataset of images concatenated with that law placing gradient. A confusion matrix provides a good measure of overall model performance on unseen data in terms of number of true positives and false positives predicted by a classifier. The test dataset consists of 100 images of each class. The confusion matrix shows that the model is quite accurate in predicting beautified and real images correctly. However, in case of predicting fake images, it has way lower accuracy and incorrectly predicts a lot of fake images to be under the real category. In order to improve fake class prediction, it might be required to train the model on a much larger dataset. Thank you.